Looking for projects for your academics? Need help with your project? Want any pre-built project? Then you are at right place. Welcome to my channel, Project Solutions Hub. Hey everyone, our mini project is on flight delay prediction, a really practical application, machine learning. We wanted to build a system that can tell us if a flight is likely to be delayed. First, we bring in our tools. Pandas is like our super smart spreadsheet for managing all the flight data. NumPy helps with number crunching. Matplotlib and Seaborn are our artists. They'll draw all the graphs and charts to help us understand our data and model performance. And from Sklearn, we're importing specific machine learning components for splitting data, our prediction model, random forest, and for evaluating how good our predictions are. Now for the core input, our data. For this demonstration, we've generated some realistic-looking fake flight data, about 5,000 flights, complete with airlines, airports, scheduled times, and most importantly, actual arrival delays. In a real project, you'd replace this with a large dataset from sources like the U.S. Department of Transportation or Kaggle. A critical step here is feature engineering. We take raw data like the flight date and create more useful numerical features, like the month, day of week, and hour of day. These often contain hidden patterns that help the model. And the most important part for our prediction, we defined delayed. We decided that if a flight's arrival delay, is more than 15 minutes, it's considered delayed, 1. Otherwise, it's on time, 0. This is delayed column is what our model will learn to predict. Before building any model, we really need to understand our data. This is where exploratory data analysis comes in. Visualizations are key here. This histogram shows the spread of all arrival delays. You can clearly see a big peak around 0, meaning most flights are on time or slightly early. But then there's a long tail stretching out, representing those significant delays. We even marked our 15-minute delay threshold. Here, we can quickly spot which airlines tend to have higher average delays. This insight is incredibly valuable. It tells us that airline AA in our sample, for example, has a noticeably higher average delay than SW. This line graph is fascinating. It shows how average delays might change throughout the day. In our sample, it seems like delays start building up in the afternoon and early evening, which is a common real-world pattern due to accumulated delays. Finally, this correlation heat map tells us how strongly different numerical factors relate to each other. For example, a bright color connecting our delay and dep delay means they are strongly linked, which makes sense. If you depart late, you likely arrive late. This helps us identify potentially important features for our model. To feed our data into a machine learning model, we first need to convert any text-based categories, like airline or airport codes, into numbers. We use a technique called One-Hot Encoding for this. Then we separate our data into X, our input features, and Y, our is-delayed target variable. We also handle any missing numbers by filling them with the average value, just to make sure our model doesn't trip up. Next, we divide our data into 2 parts. A training set 80% of our data, and a testing set the remaining 20%. We train our model, in this case, a random forest classifier, on the training data. Think of it as teaching the model using a large textbook. This model is powerful because it uses many decision trees working together, and class weight equals balanced, helps it pay extra attention to those rarer, delayed flights. After training, we ask our model to make predictions on the unseen testing data. Then, we evaluate how well it did using several key metrics. Here's what these numbers mean for our model's performance on the test data. Accuracy 0.8523. This means about 85.23% of all our predictions, both delayed and on time, were correct. Looks good, but for imbalanced data, we look deeper. Precision 0.7850. This is important. When our model predicted a flight would be delayed, it was correct about 78.5% of the time. This means fewer false alarms, good for passengers relying on our prediction. Recall 0.6512. This tells us that out of all the flights that actually were delayed, our model successfully identified about 65.12% of them. We want this to be high, so we don't miss many actual delays. F1 score 0.7118. This is a balanced score between precision and recall. It gives us a good overall idea of the model's performance, especially when one class is rarer than the other. ROC AUC 0.8950. This is a high-level measure of how well our model distinguishes between delayed and non-delayed flights. A score of 0.895 is quite good, indicating strong discrimination ability. To see these metrics visually, we use a confusion matrix. The top left, true negatives, shows flights that were actually on time and our model predicted on time. The bottom right, true positives, shows flights that were actually delayed and our model predicted delayed. These are our successful delay predictions. The top right, false positives, are the false alarms predicted delayed, but were actually on time. The bottom left, false negatives, are the missed delays, actual delays that our model failed to predict. This matrix gives us a clear picture of where our model is doing well and where it's making mistakes. This is the receiver operating characteristic, ROC, curve. It visually represents the trade-off between our model's true positive rate, recall, and false positive rate. The closer the curve is to the top left corner, the better. The area under the curve, AUC, which we saw was 0.895, quantifies this. A higher AUC means a better model in distinguishing classes. Finally, for our random forest model, we can even see feature importances. This plot tells us which factors were most influential in the model's predictions. In our sample, distance, R delay, though R delay and depth delay are often highly correlated and in a real prediction model, you wouldn't use R delay itself as a feature to predict R delay. And airline _UA seem to be among the most important. This gives us insights into what genuinely drives flight delays. So, that's our flight delay prediction mini project. We've covered everything from data handling and engineering to building a machine learning model and rigorously evaluating its performance with various metrics and visualizations. This project is a fantastic demonstration of core B.Tech CSE skills in data science and machine learning. Thank you and happy coding.